You know, it's funny. I was thinking the other day,
Yeah.
we interact with materials every single day, right?
Oh, yeah. Constantly.
But I've never really stopped to think about, like, why honey drips so slowly,
Boy, Chris.
or why a rubber band snaps back. It turns out, like, those everyday things are actually these little windows into this fascinating world of material properties.
That's right, yeah.
So, in this deep dive, what we're going to do is unpack some excerpts from a physics text that you shared with me. It's called The Physical Principles of the Quantum Theory. It sounds a little intimidating, I know,
Yeah,
but we're going to break it down, pull out the interesting bits.
absolutely. And try and make it easy to digest.
So we're going to be exploring how materials behave under stress, from like concrete to even some really cutting-edge technologies.
Yeah. It's kind of amazing how often we just take these properties for granted, And I think this text really does a good job at diving into this sort of hidden dimension of complexity.
Mm-hmm.
Revealing how these fundamental forces that are at play dictate whether a material bends or breaks or flows or fractures even.
Okay, so let's start with something that I've always wondered about. Why is it that some materials, like say a spring, bounce back to their original shape after being stretched?
Yeah.
But then other things, like honey, they just stay deformed.
Yeah, it's a great question. It really gets to the heart of this difference between elasticity and viscosity.
Okay.
So the text lays the groundwork by, first distinguishing between these elastic materials, so those that behave like a spring,
Right.
and then the viscous materials, which are the ones that deform permanently.
Mm.
So you can think of it this way, like in elastic materials, the molecules are like little springs themselves,
Oh, interesting.
always trying to return to their original positions. But with viscous materials, the molecules, it's more like they're like marbles, rolling around, so they can easily change their arrangement.
So the spring is always trying to like snap back to where it was, whereas honey just goes with the flow, so to speak.
Exactly, exactly. And the text even goes deeper, and it delves into specific types of materials that really represent these properties well. So like the Hooke solid would be for elasticity, and then a Newtonian liquid for viscosity.
Mm.
So these are kind of like the textbook examples that help us understand these fundamental principles.
Okay, that makes sense. But I'm guessing in the real world, it's not always quite that black and white, right? What about like cement or glass? I mean, those don't seem to fit neatly into either category.
You're absolutely right. And that's where things get even more interesting, I think.
Okay.
The text introduces these kind of mind-bending concepts, right? Elasticoviscosity. Have you heard of this?
No.
And firmoviscosity. And these describe materials that are a bit of both, a combination of both properties.
Wow, a combo.
Yeah. So imagine like stretching a rubber band.
Mm-hmm.
It is technically elastic, but it doesn't snap back immediately, right?
Right, yeah.
It takes a little time.
It does, yes.
So that's that delayed elasticity.
Interesting.
Or think about something like silly putty. It can bounce like a rubber ball, but you leave it on a surface, and it'll slowly ooze and flow.
Wow. So even a rubber band is more complicated than I thought. It's like materials have a memory, like they remember their shape.
Yeah, exactly, exactly. And this concept, I think, it has huge implications for the way we design and engineer everything, like from buildings and bridges to airplanes and spaceships.
Okay, so you've officially blown my mind. But get this. The text also suggests that liquids, yes, liquids, can actually have strength. I know it sounds crazy, but apparently something like water, under the right conditions, could theoretically withstand these incredible forces.
It's pretty wild, right? It's a very fascinating concept. It challenges, I think, our usual understanding of liquids.
Yeah.
But think about it this way. At the molecular level, right? The forces between these liquid molecules are incredibly strong.
Okay.
So in theory, those forces should allow them to resist certain types of stress without just flowing freely. The text uses this really cool analogy. So imagine a vessel, like a container, with tiny holes in it. And it's submerged in a liquid, and there's some overflow.
Okay.
Now, the liquid doesn't just pour out of those holes, right? It's held back a bit by its own internal strength.
So it's like there's this potential strength there that we just don't usually see because, I don't know, other factors come into play.
Exactly. Things like surface tension or impurities, they can trigger the flow.
Yeah.
But it raises some interesting questions, right? Could we actually harness this liquid strength? Could we use it to develop new materials, new technologies? Does it play a role in biological systems,
Right.
like how sap rises in trees, for example.
Oh, wow.
There's a whole universe of possibilities here.
We've gone from springs and honey to talking about the strength of water. I can't wait to see what else we discover in this deep dive.
Me too.
Okay, so we've talked about elasticity and viscosity, and even liquid strength.
Right.
It's pretty wild.
Yeah.
But I have a feeling we've only, scratched the surface here
Oh, yeah, there's so much more.
of what this text has to offer.
Absolutely.
Right.
Let's
What else is there?
let's delve into the world of concrete,
Okay.
a material we encounter literally every single day,
Yeah.
but rarely stop to think about
Totally.
how complex it really is.
Perfect. Because I've always been curious about concrete. It seems so simple, right? Like it's just cement and sand and gravel.
Right.
But I'm guessing there's more to it.
Oh, way more to it.
And that meets the eye.
Yeah, concrete is a fantastic case study, I think, for how a single material can exhibit multiple of these rheological properties,
Oh, big word.
which is just a fancy way of saying
So,
how
yeah.
materials deform and flow.
Got it.
So, for instance, concrete, it can behave like a hooked solid, exhibiting that elasticity when it's subjected to, like, short-term loads,
Yeah.
like a truck driving over a bridge.
Mm.
But it can also act like a Maxwell liquid, where it slowly creeps over time.
Wait, hold on. Concrete creeps.
It does?
I thought only insects did that. What
Well,
does that even mean?
so imagine, like, a concrete beam
Okay.
supporting a roof.
Mm-hmm.
Over many years, that beam will actually sag ever so slightly
Really?
due to that constant force of gravity.
Oh, wow.
That's creep in action. It's a time-dependent deformation that happens under constant stress.
Interesting.
And get this, it can even behave like a burger's body,
A burger's body. What's that?
which exhibits delayed elasticity.
So, wait, it takes its time to decide how it's going to respond?
It's pretty amazing.
That's wild.
And what's even more fascinating is that the rate of creep in concrete can be affected by something that you might not expect.
Air? Air. You mean like the stuff we breathe?
The very same.
What does that have to do with concrete?
It turns out that tiny air bubbles
Okay.
that are intentionally introduced into the concrete mix play a huge role in its properties.
Interesting.
These air pockets, they act like miniature shock absorbers.
Oh, cool.
They improve the concrete's resistance to cracking from those freeze-thaw cycles
Oh, right.
and make it more durable over time.
Huh. Who knew? Something invisible could have such a big impact.
Pretty wild, right?
Yeah.
And the text even delves into this groundbreaking concept of volume flow in concrete,
Volume flow. Okay.
explaining how the material can actually flow into its own pores over time.
Wait, so concrete's not just a solid block?
Right.
There's space inside it.
It's not perfectly solid, no. It has these tiny voids and spaces
Okay.
within its structure. Over time, the solid parts of the concrete can migrate into those spaces.
Wow.
And it causes subtle shifts in its shape.
So even though concrete seems rock solid, it's actually constantly changing
It is.
at a microscopic level.
Yeah, and evolving.
That's incredible.
It is pretty remarkable.
I'm starting to see why material science is so fascinating. There's so much going on that we just never even notice.
Right, that we completely take for granted.
Yeah.
Happening right under our noses
Exactly.
to dive even deeper.
Okay.
Let's revisit the Weissenberg effect.
Oh, yeah.
Remember that?
But one that kind of messed with my head.
Where the liquid seems to defy gravity,
Right.
climbs up a rotating rod.
It's like out of a science fiction movie.
Right. It's a great example of how simple, sheer,
Okay.
the kind of force you use when you're spreading butter on toast,
Okay.
can lead to these unexpected forces that are perpendicular
Wait, hold on.
to the applied force.
I'm trying to picture this. So, if I'm spreading butter, there are forces going sideways.
Exactly.
Not just down.
Not just down.
Oh,
Yeah. And in certain materials, like polymers, these sideways forces can be quite significant
Interesting.
and lead to things like rod climbing or die swell, where materials expand after leaving a die.
So that's like those weird stretchy things that polymers do. That's the Weissenberg effect in action.
That's it.
Hmm.
Understanding this effect is crucial, I think, for designing and processing these polymers effectively.
So it's not just a theoretical thing, it has real-world applications.
Huge applications, from plastic films to packaging to advanced materials used in aerospace and medicine.
Wow, so this bizarre thing is actually really important in our lives.
It's everywhere.
It is
You
everywhere.
just got to know what to look for.
Yeah.
Are you ready to dive even deeper
Bring it on.
into this rabbit hole of material properties?
I'm all ears. My mind is ready to be blown again. I mean, my brain is like still buzzing from all these mind-bending concepts, you know?
Yeah.
I'm starting to see the world around me in a whole new way.
Okay.
It's like everything from the concrete sidewalk to the plastic containers in my kitchen. I'm like, whoa, there's so much more going on than I ever realized.
Right. It's really amazing how much we just sort of take for granted
Yeah,
until you really start digging into it.
exactly.
So what other like hidden wonders? Yeah. What else is there?
Does this text have in store for us?
I'm ready.
Well, how about this?
Okay.
We've been talking about, you know, volume and shape
Hmm.
as if they deform kind of independently, right?
Yeah, like squeezing something changes its volume.
Right.
Twisting it or shearing it changes its shape.
Exactly.
Okay.
But what if I told you
Okay.
there are materials that kind of defy that simple separation?
Okay, now you've really got my attention.
Yeah.
What kind of material does that?
So the text talks about this fascinating phenomenon called dilatancy,
Dilatancy. Okay.
where a material's volume can actually change
Okay.
when it's subjected to shear stress.
Okay.
So think about walking on wet sand at the beach.
Okay.
Have you ever noticed, like, as you step, it seems to dry out?
It does, yeah. Around your foot.
Yeah, that's because you're applying shear stress to that sand.
Oh, interesting.
And the sand grains,
Hmm.
they rearrange themselves in a way that increases the space between them.
And so there's less space for the water, and it looks drier.
So squeezing the sand actually makes it expand.
It does, yeah. It's pretty counterintuitive.
That's wild.
Right. And this isn't just limited to sand. This can occur in other materials, too, like clay, even some elastic solids.
Mm.
It all comes down to how those particles within the material interact
Yeah.
with each other
Okay.
under stress.
So even something as simple as stepping on the beach can teach us about material properties.
Exactly. It's all around us. It really is.
That is so cool.
And speaking of discoveries,
Okay.
remember our discussion about creep,
Oh, yeah, that slow, time-dependent deformation.
right, that we see in concrete.
Yeah, I'm still wrapping my head around that whole idea that concrete can, like, slowly sag
Yeah.
over time.
Well, it turns out
What?
creep isn't just like a simple flow.
Okay.
It's a complex interplay of all these factors, right? Elasticity, viscosity, and even the internal structure
Oh,
of the material.
So it's like a slow-motion symphony almost, with all these different things happening.
That's a great way to put it.
Yeah.
And the text points out that the rate of creep can be influenced by so many different things, like the mix of ingredients in the concrete, the amount of moisture, the temperature.
So every concrete structure's got its own, like, unique personality almost?
Yeah, kind of.
Yeah.
Shaped by its composition in the environment.
That's fascinating. This whole deep dive has been incredible.
It has been a wild ride.
And we went from, like, basic elasticity and viscosity to, like, liquid strength and dilatancy.
Right.
What would you say is the biggest takeaway you want listeners to remember?
I think, honestly, the biggest takeaway is that the world of materials is just far more complex
Yeah.
and
Yeah,
interesting
we realize.
than we realize. Yeah.
Yeah.
And by understanding these like fundamental properties and how they all interact,
Yeah.
we can not only, appreciate this sort of intricate beauty of the physical world, but also unlock like countless possibilities for innovation and problem solving.
It's not just, like, abstract theory.
No.
It's about using this knowledge to make things better.
Exactly. Material science is at the heart of so many advancements.
Yeah.
From new medicines to building materials to like pushing the boundaries of aerospace engineering.
It's an inspiring thought to end on.
It is.
Well, thanks for joining us on this incredible deep dive into the world of material properties. Until next time, keep exploring, keep questioning, and never stop learning.